Hello, welcome back. In this video, we're going to try to determine if the given function has a vertical asymptote or removable discontinuity. Because these two things are confused by the students, and we're going to investigate this for the given rational function x squared minus 1 divided by x plus 1, and the point that we're talking about is x equals negative 1. Right, for the existence of a vertical asymptote, we're going to look for an x value for which the bottom of the rational function is 0 but not the top. And here the point is x equals negative 1. So let's just write the top and the bottom separately. And the top is x squared minus 1 and the bottom is x plus 1. So at x equals negative 1. The top is minus 1 squared minus 1. This is a quantity square, so it ends up 1 minus 1, 0. And the bottom turns out to be 0 as well. So you're talking about what? 0 over 0 type indeterminate form. And in fact, this kind of form is not a good candidate for a vertical asymptote. And at this moment, we should do some algebra here. To sort of like dive into this situation deeper. So as you see here, you have x squared minus 1 divided by x plus 1. Well, from algebra, we remember that we can factor the top because this is difference of the squares. And the top can be rewritten as x minus 1, x plus 1 divided by x plus 1. So in fact, around the point x equals negative 1, but not x equals negative 1, we can do the cancellation, and then we can just say like this function is equivalent to x minus 1 for every x except negative 1. Because I know that for negative 1 the function is not defined. And for negative 1, you have 0 over 0. I'm not allowed to divide 0 by 0. So except negative 1, the function is exactly equal to x minus 1. So that's good news because this function can be simplified into x minus 1. And this function is perfectly defined at x equals minus 1. That essentially tells us that we do not have a vertical asymptote at x equals negative 1, but we may have a removable discontinuity because we can redefine the function so that we can make the function continuous. So I redefine the function as x is not equal to negative 1, and for x equals negative 1, I can define the function to be the limit value, which was that is equal to negative 2, right? Because I replaced the function, this function here, by x minus 1, and at x equals minus 1, I can use that function to redefine f. So f is this way redefined as a piecewise function. And as you see, continuity is in our pocket because if you approach x equals negative 1 from the left and right, you can get down to the limit value negative 2. And that's in fact what the function value is because that's how we redefine the function. And since the limit value is exactly the same as the function value, we can conclude that the redefined function is continuous, even though the given function was not. So x equals negative 1 is a removable discontinuity point. The graph of x squared minus 1 over x plus 1 is this blue line. And whenever you hit x equals negative 1, there's a hole here because the function is not defined. And what we did when we redefined the function is to fill this point so that the value of the function becomes negative 2 here. So this way there's no break in the line when you start graphing it. There's no hole, there's no gap. So the resulting function is now continuous. All right, thanks for watching. This is the end of the video. I'll see you in another video.